Um, call to order. We will now talk about Zig for the first time all hour. Thank you for coming and joining us at Utah Zig, the most unsafe meetup in Utah, nay, the world. And also thanks to Vivint for hosting us and providing pizza. And with that out of the way, we're going to turn some time over to Niles to talk about whatever he wants to talk about without interruption or questions. Andrew.
Yeah, so I have a 5-minute talk. We'll probably get through it after 2.5 hours.
And then after that, we'll go back to the last 3 minutes.
Yeah. So,
if there's time before the heat death of the universe.
yeah. I accidentally looked at the sun. All right. So, today at my work, I work for TV Scientific. That is an Atlassian thing.
I was like, well,
Let's do that. I work for this company. It is ad tech, but also we don't do like gambling stuff or nothing too bad. There are people that we turn down. We have a system where companies come to us and they're, looking for these outcomes, So as part of that, we deal with protocol buffers. And we do have an internal protobuf implementation for Zig. It has not been open sourced yet. I think we would like to at some point. I did not write it, but I did come up with an optimization the other day, actually during a performance review, where they're like, you're pretty good at this optimization stuff, and we could really use that for protobuf. And I'm like, let's pull it up right now. So that was last Friday. And so in protobuf, there is some encoding stuff that is absolutely brilliant, if I must say. They have what are called var-ints. So they have the number 150 represented right here in hex. And it's 3 bytes. Why is it 3 bytes? Well, it's because they allow unsigned 64-bit integers using anywhere between 1 and 10 bytes, with small values using fewer bytes. How it works is each byte in a var-int has a continuation bit that indicates whether the byte is part of the var-int. So the most significant bit of each byte, i.e. the sign bit, tells you whether to keep going and look at the next byte. And you get 7 bits of payload per byte. So if you have a byte like this, these 7 bits are your payload, and then this bit tells you whether to grab the very next one. Likewise, right here we have 150. We have 7 bits of payload right here, and they actually rendered it backwards. So this is the first byte. I'm sorry. So this is the first 7 bits. This is the continuation bit telling us to grab this byte. I don't know why they did it in this order. And then this tells you whether to grab the next one. This is a 0. And so we're not going to look at the byte after this. But we have 14 bits of payload in here that we have to put together. So how do you figure out this is 150? First, you drop the MSB from each byte. It's basically what I just told you. The signed bits you discard, and then you concatenate it. And when you interpret it as a 64-bit integer, you get 150. What's up?
does that mean negative numbers will take a lot of bytes?
Yes. Yes. So for anyone who doesn't know, 2's complement numbers, in order to have a negative number, what you could do is you could have the uppermost bit be a sign bit, but in 2's complement, they actually make it a power of 2 as that negative number. And so if you have like an 8-bit signed integer, you have a 1's place, a 2's place, a 4's place. 8's 16s, 32s, 64s, and then you have negative 128 if it's a signed byte. And so this gives you a range of negative 128 to 127. And that's basically how 2's complements work. It's nice because if you just do like regular addition and subtraction with it, when it overflows across the zero boundary, it correctly handles the case. Like if I have negative 1 plus 2, I'm going to get positive 1. So it's a cool trick, and that's how signed integers work. And yes, so if you want to encode a signed integer, you need a 1 in the uppermost bit, and usually a lot of 1s underneath it as well. If it's negative 1, it's going to be a bit string of all 1s. And if you want to encode that, well, with this, you need 10 bytes in order to encode negative 1. So that's kind of annoying. And yeah, I'm pretty sure that that is one of the drawbacks of this. I did not invent this. This is a Google thing that they pushed. Oh yeah, here you go, signed integers. So actually, yeah, I think they might have a special way of doing it. So they have a zigzag encoding. I actually didn't write the code for this. So they can, yeah, they do a really smart thing with this. Yeah, I should have gone through the whole thing here, but
He actually read it before.
okay. But yeah. So anyways, I did solve this problem of doing var-int decoding fast. So originally we had a loop where we went one by one, and we're like, okay, look at this byte. If it's greater than or equal to 128, i.e. the most significant bit is set, grab the next one, and then you just have a result, and you just OR things into that result. Hopefully everyone would know how to write that. It's annoying, but it's not hard to write. I ended up writing a branchless version here, which is pretty cool. So I want to show how this works. So first thing I do is I just read in 8 bytes and 2 bytes after those 8 bytes. Obviously in a real application, you have to make sure that it's safe to do this, that you actually have enough allocated, that you don't run off the end of a page and go into memory that will cause a seg fault. But just for the purposes of this compiler explorer, we read in 10 bytes, and then I make this C constant that I refer to, and this is repeated 7F. So what that looks like in binary is a 0-bit and then 7 1-bits, like this. So this is what we're talking about. Okay. First thing I do is I take my first 8 bytes, A, take the not of it, and then I do and not with C. So that would be the same as OX80, this constant. And in binary, that would be 1 in the highest position and 0s everywhere else, like this. Okay. So I do A ANDed with this. So the not of A ANDed with this. So the reason why I'm doing that is because I want to check the uppermost bit of each byte, and I want to check where's the first 0, because the rule is that where there's a 1, that means I'm going to grab the next byte. So instead, what I want to know is when is the first time I'm not grabbing the next byte, so I can figure out how much I'm actually looking at. And then I do a subtraction by 1. Okay. Does anyone know why I do a subtraction by 1?
Is that underflow?
Say it again?
Is that underflow?
No. So the reason why I would want to do this is,
So you get 1 at the start.
so
So you know how much.
let me put the question in maybe a more answerable way. When I subtract 1 from a number in binary, if I were to write a loop that does that, what would that loop look like? Like if you wrote a loop to implement -1, what would it do?
It
would just go, it would be for every bit in the binary, if bit equals 1, set to 0. If bit equals 0, would you carry that over? Or?
Mm-hmm.
Yeah.
So starting from the least significant bit position, we would say while we see a 0 bit, flip it to a 1. And once we hit a 1 bit, we set that to a 0 and we break.
Oh, okay.
That's the algorithm for subtracting 1 from a binary perspective.
Okay.
And so we can do this to figure out where the first of something is.
That's crazy.
Okay? So yeah, you can think of this like a loop.
Yes.
So yeah, hopefully people saw that who wanted to. But yeah, so the first thing that we do is we want to figure out where is that first 1 bit, and we get a mask under it. So let me take a copy. So I'll show it again if anyone missed it. So when we subtract 1, the rule is it's while we see a 0 in the least significant position, replace it with a 1. When we see a 1 bit, 0 it, and break. That's the loop that I'm talking about. And so then we can do, we can take that value and we can AND it with that same bit string as before, which is this one. And so this will tell us how many continuation bits we happen to use. And so in this case that I showed, if we happen to have one where the very first bit, the very first byte doesn't have a continuation bit, we would end up with 0 in here. We would pop count that. Pop count means count the number of 1 bits, and then we would add 1. And this tells us how many groups of 7 bits we're going to keep, or how many bytes have payloads that we want to keep. If I give another example, let's say that we had some bit string where we got something like this. There were some zeros in here. And remember, this is inverted from A, because a 1 bit in the most significant position in A tells us to grab the next one. I take the naught of it, so now it's going to be zeros. And now a 1 bit tells me to stop. And so I want to know, where do I stop? Where's the first 1 bit where I stop? And so when I do a subtraction by 1 here, I get a 0 followed by 1s. I figured out I cannot hold 1 on this computer and make it just print 1s, so I have to do each one. Okay, and then when I do the AND, sorry, let's put it back. Then when I do an AND with this literal bit string, then I'm going to get an answer which is like this. So it's just going to tell me which continuation bits I hit, like which continuation bits in a row are 1, starting from the front. And so that's what I've covered so far. And then we pop count it, like I said, and there are 3 of them, and we add 1. So that tells me there are 4 bytes that we're interested in, which makes sense. We have 3 continuation bits, and we always take the first byte, and so that gets you to 4. Okay, so what do we do then? There is one more byte that we can't account for within the 8 bytes that might have a continuation bit, because we can be up to 10 bytes. We can have 8 continuation bits within the first 8 bytes, but then we have 2 bytes off in the end. There's 1 continuation bit in there we want to look at. And so this is the position it's in, right? Shift to the right by 7, and then we want to know, using this bit string that we had before, did we actually have a continuation bit at the end that is still part of the run of continuation bits? And so this will get us a 1 or a 0 value that tells us whether we need to preserve a byte or a single bit in the uppermost 10th byte. What's up?
Doesn't Zig have arbitrary length integers? Could you interpret the 10 bytes all as one integer and do it that way?
You could. You could use a U80, but I tend not to do that because you're trusting the compiler to do the thing that you want, and I don't. Because the nice thing about it is you can tell it like, okay, take this whole integer and do this operation. But like, if you look at this logic right here, the compiler would not implement it this way probably because it would have less information about what I'm interested in. You know,
Okay.
if the logic was in there that it could figure this out, like theoretically it could, but when I specify what I want it to do, I'm way more likely to actually get it to do what I want. And so usually I just use U64s, U32s, that's it. Sometimes U16s and U8s, but yeah. I did have this commented out just for the sake of the Godbolt here, but I do use this as well. So we figure out how many continuation bits there are in the first 8 bytes. We figure out whether there's a continuation bit in that 9th byte that tells us to grab the 10th one. And then we can produce this to say how many bytes we consumed in total. So yeah, this will be a value 1 through 10. And we can use this in the real code to skip over how many bytes that we actually read, that we actually consumed, I should say. And then we also want to know how many bits are we preserving. So I wrote it in kind of a dumb way here. You might know how you could simplify this. But I said 8 times num groups of 7 to keep plus preserve 1 bit in 10th byte minus num groups of 7 to keep. How would you simplify that, perhaps? This is an algebra question. Elementary school algebra.
Times 7 instead of times 8?
Yep. So you could do that way, but LVM doesn't give me the emit that I want when you write it this way. So if you look at the assembly over here, I don't know how much assembly everyone has looked at, but on x86 we have this LEA instruction. That stands for load effective address. And this instruction is an accelerator for usually, or a lot of times I would say it's used to calculate an address. So you can add 2 or 3 numbers together, and then you can also stick a bit shift or a multiply is how it's rendered. A bit shift by, of course, 0 or 1 or 2 or 3. And that will be rendered as multiplying by 8 on here. And so this is just, it's just an instruction that's, you know, it allows you to do in one instruction something that you have to do very commonly, which is, you know, if you have a pointer to the start of an array and it's 8-byte elements, and then you have an index where you're like, okay, I want to go to index 4, how do you get there? Well, you have to do 4 times 8 plus the start pointer. And so this instruction lets you do all of that in one instruction. And because it's so common, it makes a ton of sense to have an accelerator for this. So the thing that I notice when I see this is that we're using it to multiply by 8, which is fine. The other way that it could have done it is, let's see if I can just type right here. I'm hitting the wrong button. It could have done a shift right on RDX by 3. It could have done this, but the destination would have to be the same as the source. And so another thing that this instruction is used for is as an instruction that has a separate destination from the operands. And so that means, because yeah, a lot of your things in a non-RISC architecture in x86, it's instead of, like, you have an add instruction, but it's really more of a plus equals, like is how you'd write it in Zig or something. And you have minus equals, and you have multiply equals. This one actually has some more caveats, but but yeah, the point is, yeah, you can see right here, shift right by 7. And so this, it pulls from ECX and it writes it back to ECX. And so if you want to have a separate destination without needing a move instruction, one thing that the compiler can do is sometimes it can use this instruction. So yeah, this happens like if you want to add two numbers together. Let's just do it.
I do that all the time.
Because I'm in front of everybody. All right, so yeah, when you add two numbers together, it could use add, but because these are in two separate registers from what it wants the destination to be, it can do LEA and still do it in one instruction. This is just ABI stuff. I don't know why it started doing this, because at one point it didn't show the ABI stuff. But yeah, this is the one instruction that it actually generated. Anyways. So, and there are other like interesting things too. Like you'll notice the and not instruction has 3 registers specified. 2 of these are sources, 1 of these is a destination. Whereas and, you have 2 registers, 2 sources, 1 is a destination as well. And so the reason for this is because this and not was added later, and this and was part of the base instruction set way back in the day. And so there are some cases where, like, if you wanted to avoid a move, you could use and not rather than and, if you can invert this, you know, if you can invert it earlier or whatever. So it's x86, it's hard to optimize for sometimes because there's a whole bunch of optimizations you can do like this. And so, like, yeah, you'll...
Is that why Intel's like changing their architecture, or is that for something?
Not really. Intel is, so like if you're talking about the new stuff that they just published specs on within the last 2 years, they want to make it so more code can be made branchless or remove more branches. So if you're talking about like the conditional condition updating instructions, that's what that stuff is for. It's trying to reduce how many times you need a jump on equal or a jump on true or whatever. So anyways, the problem with this code is that this add instruction can be folded into here. But there's a subtraction here that kind of doesn't help it. So what is it doing? When you multiply by 7, a lot of times, okay, that it's the same as multiplying by 8 and then subtracting, right? So 8x minus x is the same as 7x is what I'm trying to say. And so if I write a function like, let's do it again. There you go. So if I write this, let's actually just start with multiplying by 7. You can see we multiply by 8 and then subtract 1. So this is just 8x minus x. This is just more efficient than doing a multiply because you can do this in 1 cycle, you can do this in 1 cycle. Multiply takes 3 cycles. So there you go. Blazingly fast. All right. If you do a subtraction, or sorry, we were adding this one. So what I want to see is I want to see this folded in, but it isn't. And if you do 8, you can see how this folds in. And then if you write it like this, it folds it in properly. Why is this the case? Well, I think it's because Zig doesn't specify that the parameters are no undef when it passes it to LLVM. So when you go in here, this is what the LLVM IR is. So this is what LLVM sees.
Intermediate representation for those not
Yep.
in know.
Yep. And for C, I don't have a local instance of C, but we can use the internet.
I don't know, you didn't install it.
Yeah, I didn't install Or I just don't have it set up quickly.
Yeah.
But if I convert this to C using ChatGPT,
Oh.
Oh, you have accepted.
I don't know. Thank you. It's just quicker than typing. So let's turn on optimizations. Let's go to target. Say 664 Linux M-Tune. Let's do it like that. And I messed it up like one does.
As one does.
I accept this part. I'm not gonna do it.
Oh my gosh.
And Objective C, I remember I was doing the end cleans in that for the things I wanted to use metal. And the O3 thing did nothing. And it like, the launch time, the runtime, nothing, it affected the performance.
I don't know how
Not
to
at
change
all.
the target on
I
claim.
was like, oh.
Well, this is GCC. Of course it doesn't work.
Oh,
I meant no offense by that.
ouch, because that felt really offensive. It's a good thing that it's not a safe place here. Someone could have gotten hurt.
Let's try it one more time. Okay. So, when we try the same thing in C, it gives me the right emit for some reason. And yeah, if you look at the LVM IR,
It's empty now.
it specifies no undef. And Zig does not. I don't know why the C compiler does. There are people who are still debating this. So if you have issues, sometimes that's to blame. Although, oh yeah, I clicked X out before you got to look at it. But yeah, so I don't know why this is the way it is. It's kind of annoying to me. But yeah, C, go ahead.
What does no one do aside from that optimization?
So basically, you're specifying that you can't pass in undefined and you can't return undefined. And the problem is that undefined has different truth tables. And so this enables some optimizations that, yeah, for some reason, if you do not put this in here, yeah, it assumes that undefined could be passed in. So it's like opt out rather than opt in. And
So undefined is different from null, right?
correct. So undefined is a value where it's an error to access it
Right.
in Zig. Obviously in like JavaScript it's different. It's a value that's not, well, yeah, it's hard to describe, but it's a value in JavaScript, right? But here we're not talking about a value that you can access at all. If you touch it in any meaningful way, it's an error, is what undefined means. Okay, let's just close that. So anyways, so that was the reason why I wrote it like that. If we go back to this, you can see we had load effective address, subtract, and add. If I do multiply by 8, and I subtract, then we get the optimization here that it's going to fold one of the adds in. And then you can see that it adds 8 here. And that's it trying to be smart because I added 1 right here. And so what I like to do is try to keep it from being smart because it's really not. And we can put parentheses around this. And we can do or 1. And so we can do the increment because in here, like we're doing an and on a bit string where the uppermost bit of each byte is set to 1. And so we know the lowermost bit is not set. And so I can set that bit, and then when I do a pop count, it'll be 1 higher. And this will disable LVM from seeing it and trying to be too smart. It will change my OR to an increment. So good job. It did figure that out. It also inserts an XOR here before doing a pop count now. So this is just the register allocator not being smart. But yeah, it's a house of cards, everybody. I hate to tell you.
So, okay, but at what cost? Right? because you're doing something here that is very non-intuitive and would require, I mean, all right, so I'm gonna make an assertion here. I think that you are smarter than most people and have better pattern recognition and algebraic pattern handling than most people. So when you look at this, one, you've got the experience of what you've done.
Mhm.
And two, even if you didn't have the experience of what you've done, you have not unique, but you are in the upper tier of people that are able to look at something and distill the pattern and the algebraic complete operation. So if the goal is literally, we want to save every single CPU cycle that we can on our target CPU,
Mm-hmm.
then like, yes, 100%, this is what we got to do. But, I mean, essentially you've written regex, right? Like, you wrote it, no one else will ever be able to read it or edit it. I mean, that's not entirely true, but like, is the instruction count that you're saving here,
Mhm.
is that the, what's the opposite of the straw that broke the camel's back? Like, is that like the grain of rice that made the sail?
Well, we do care about protobuf parsing speed, and yeah, if this can make it faster, which I'm actually going to test it on the production machines today. Yeah, we have a copy of production that I can test it on. Where yeah, so I won't be like taking down production to test it, but yes. The other thing is, I mean, yeah, in terms of having a couple of and nots and a -1, that is something that someone would have to learn. But in terms of what values we're producing here, like the number of groups of 7 to keep, whether we preserve that 1 bit, I think this is as understandable as I can make it. How many bytes we consume, how many bits we actually need to keep around.
Well, what I'm saying is like, for example, I mean, I guess you could expand out this or 1 maybe into a variable to make it more clear that what you're trying to do there is actually add 1 but trick the compiler. But then again, maybe pulling it out of a variable might cause it to de-optimize it or something.
Well, it won't. You can also make it add 1 and it's the same thing. But that was just for demonstration purposes.
Okay.
I'm just here to teach something, that's all.
I'm just saying, like, where do you, if you have to save every cycle, yes. It just, I don't know. I guess I would not be the one doing this work. And the person who's doing this work has already got all this other stuff on top of their head, so it probably would be obvious to them. I'm just
Okay.
devil's advocate, or maybe angel's advocating a little bit.
Okay.
This would be like premature optimization.
Well, it's not necessarily that it's premature. It's like at what cost? Because at some point we have to decide to let something be. I mean, I guess if you write perfect software, which I think is part of the goal of Zig to a degree, right? But that's why you get so much control. If you write perfect software, then you only have to write it once. You don't have to have 1 billion implementations.
That's me.
Because once you have written the algebraically perfect piece of software, and you've accounted for any weirdnesses in the way that the compiler is going to interpret or whatever, then it is done. No one else ever has to read it. So, I mean, there's that too.
Yeah.
I mean, the other thing is that like comments don't take up like CPU cycles, and you can just like completely fill this with comments to like explain everything that you're explaining right now.
So the problem with that is that the comments don't move with the code. It would be interesting to see what it would look like to have a programming language that somehow had semantic meaning and comments, that the comments would move with the code. But what you will find, 6 months into a project, is that there's a comment to do. Make sure to widget the gizmo. And then you look below and there's a sprocket. And you're like, we're gonna widget the gizmo, but this is a sprocket. Because at some point somebody did widget the gizmo, and when they widgeted the gizmo, it turned out that it was terrible. Instead of a 10% increase in performance, it was a 30% increase in crashes. and then they replaced it with a sprocket. But when you're in the mode of editing code,
Right.
you're in the mode of function, and when you're in the mode of comments, it's like two different brain pathways. And so the comments stay, and then they'll do things that look wrong. Like, I give an example I've given a couple of times. I was looking at a piece of code, and it had a number that was really close to pi, that it was multiplying by. It was like 3.14, and then like the next digit of pi, and then like a digit off. And I thought, well, that's weird. Like, how did that happen? I'll just replace this with a pi constant. Totally broke the build. and then I was like, okay, well, you know what happened there? And it was that we're dealing with an analog system, and it happened to be that the attenuation of the signal was very close to pi, because that is pretty normal. But it's like if you're dealing with something in a circuit board, like you've got capacitance and you got all this other stuff. So it's like the attenuation of the signal naturally in a perfect world of physics might have been pi, but it ended up being really close to pi. So the discovered value was close to pi. Now, if that had been put into a comment, it probably wouldn't have helped because it would have changed in times. If it had been put into a variable, then, you know, like,
Sure, yeah.
you know, like attenuation factor. If it had been put into a variable, then it would have persisted in the code. But yeah, whenever there's a comment, the comment doesn't change with the code. Sorry for derailing your 5-minute
I
presentation.
just
Yeah.
had one more comment to that. Because
Because it won't change with the code.
I come from a neuroscience background, so that problem persists with all language, all the way back to like Egyptians in their time. Basically, the idea is if you have a dictionary and you look up the definition of a horse, and it'll just say everyone knows what a horse is, and then years later, an archaeologist comes on it and they're like, oh, what does this mean? I know that's a trite example, but it happens with every language.
I know that example is from the first Polish dictionary.
Is it? Yeah.
Yeah. The first Polish dictionary under horse said everybody knows what a horse is.
Yeah. And like,
And one day there may be no horses and
yeah.
still people, and people are like, what the heck? I don't know what that means.
Well, let's see.
The author wasn't asked.
Yeah, there you go. There you go. All right, so last 2 lines of code. We use this PEX instruction. Has anyone used that before? Or know what it means?
Oh, yeah, all the time.
All the
Okay,
time?
so
Oh,
wait,
yeah.
but all right, just so we're clear, how many people in the room regularly open up Godbolt? I'm not going to raise my hand other than as an example.
Thank you for showing us how to raise hands.
Hey, not everybody's an algebraic master.
I've been doing it wrong this whole time. So
Yeah, he's doing the jazz hands on the side.
I open up Godbolt every so often, but usually I'm programming in JavaScript where it would not help if I tried.
All right, next question.
All right.
How many of you are using these things like @as or @popcount in your code?
Well, as is just a type thing.
Yeah.
Or sorry, yes.
Everybody uses that.
Well, except for those of us that only run the meetup and don't program in Zig.
Yeah. I wouldn't know anyone like that.
Yeah, you wouldn't. But JoJo does. And so we have to.
what's the @ sign mean?
The at in front of an identifier is a built-in. So built-ins that have a special meaning in the compiler and special semantics, they have an at. And so this @as is just for casting whatever it gets right here to a U64, or coercing, I should say. It coerces it, but it's not doing a cast like.
So what is the pop count coercing it to?
So the pop count is an instruction or set of instructions. It's a function that tells you how many 1 bits are in a particular integer. And so, yeah, in bit manipulation code, it's very common. But I know that most people are not doing that very often. So yeah, this is just saying, take whatever's in here and tell me how many 1 bits we ended with.
Quick question, since the number is stored as 2's complement, does that also get counted in pop count or no?
Yes, I'm just dealing with unsigned integers here.
Because I thought you were following the spec from earlier, or no, that spec just doesn't run into this issue. That's
Yeah, we're reading it inside of unsigned integers,
okay.
and we're just trying to find the payload bits.
Oh,
So you could do that other stuff on top that it's talking about, like do zigzag decoding or whatever. But right now, I'm just trying to figure out where are the payload bits. Can I get them all together?
okay.
That's what I'm trying to figure out. And we almost finished. Okay, so we figured out how many bits to preserve, how many bytes we consumed, and now we are ready for the magic, okay? So we use this PEXT instruction on A, which is our first 8 bytes, and then C, which is this constant here, which is every bit is set except the uppermost bit of each byte. So this corresponds to all of the payload bits. We also PEXT B, the last 2 bytes, with the same thing. So what does PEXT do? PEXT is a bit level compaction instruction. And so what it will do is it will, you can think of it like doing an AND, a bitwise AND, except we're not just zeroing out the values that correspond to a 0 in the second operand, we're actually only keeping the values associated with a 1. I had an animation for this in my other talk, for just what a compression looks like here. Can I do full screen? That doesn't matter. We'll just go through. So right here, what a compression looks like is this animation here. Okay. So if you have, imagine that these symbols represent a 1 and the underscore represents a 0, and we have some other corresponding thing. When it's a vector compression, we're keeping the elements, but when it's PEXT, we're just keeping the individual bits that correspond. And so this is the animation here that a compaction looks like. All of the things that correspond to a 1 bit, we keep those. Anything that corresponds to a 0 gets trashed, and there's a compression. I'll show it one more time. So this is the idea of a compression, or yeah. And so a PEXT does this. Let me close this one. So a PEXT does this at a bit level. And so when I have this bit string where it goes 0 and then 7 ones, like this, and I have some other bit string of data, I don't know, spam some numbers
That's
here.
not very random.
I know, but I'm just spamming as quick as I can. So the point is that we're going to delete the values associated with 0, and it's going to compress that value. So that's gone. This one will be deleted as well. And this one will be deleted as well. And yeah, so the point is only the bits that were originally associated with these positions will be kept around, and anything corresponding to a 0, that's gone. That information is deleted from the result, and the holes are then closed.
Right.
That's what PEX does. Kind of like this animation.
So why?
So the reason why is because inside of each byte in the protobuf spec for var ints, we have 7 bits of payload, 1 bit that tells us whether to grab the next one. We figured out how many we grab, but now we want to compress it so each of those 7 bits are next to each other without the continuation bits. So we just keep the payload information and we discard the continuation information using these 2 PEXT instructions. And so we have the first 8 bytes. We can take out 8 bits. That's the uppermost bit of each byte to get us 56 bits of payload. And then we had 2 remaining bytes here that we can extract. There's only actually 8 bits of information that we're interested in. The last byte can only have 1 bit because you can only have 64 bits or 8 bytes total. So you get 7 bytes of payload in here, 1 byte of payload in here. You shift it up to the most significant position of a U64, and you can put them together. And so this gets you 10 bytes of var int compressed into 8 bytes by removing the continuation bits. But we may have grabbed some invalid data. So to do that, to delete that, we use this bz high instruction. And bz high, you can see it right here. And here's my PEXT, 2 PEXT instructions. The bz high instruction, what it does, here's a description. It copies the bits of the first source operand into the destination and clears the higher bits in the destination according to the index value specified by the second source. The index is specified by bits 7 through 0. They always do it backwards for some reason. And the index value is saturated at the value of operand size -1. Carry flag is set if the number contained in the low 8 bits of the third operand is greater than operand size -1. Okay, so if you didn't get that, what it's saying is it looks at the lowest byte. That's what the 0 through 7 bits are. It looks at the lowest byte, and it says, and this tells it how many bits to keep. Everything above that bit position that we specify in that lowest byte is zeroed. And so right here, I pass in the number of bits to preserve. So this value will either be 7, 14, 21, 28, 35, 42, 49, 56, 63, or 64. Those are the options. And I pass that in with my payload that was 10 bytes condensed down to 8. And this tells me how many of those bits do I want to keep at the end. So if I pass in 7, then I'm only going to keep the lowest 7 bits. If I pass in 64, I keep the whole thing. And so this can branchlessly decode a 10-byte var int. So this is the SWAR version. I wrote another version, which is a SIMD version here. So let's bust out the SIMD. And let's take off the export on this so it's at the top. Okay, so there is one piece that I'm missing from this, which is the part where we decode, where we pull in the information and we figure out how much we want. So this is actually just showing how I'm masking the information. Yeah, I didn't pull up that code yet. I could, but okay. Let's just start with what I have here. So this is assuming that you already read it into a 16-byte vector. And there are nice ways of doing this. I say nice. I wrote a function that makes it nice to do this in our code base. You can call a masked load from LLVM to safely grab 16 bytes, even if there aren't actually that many bytes allocated. So it will take a slice and it will take the length, and it will actually use the bz high instruction. So what we can do is we can pass in -1 to here, and then we can pass in a number, and it will give us a bit string with that many 1 bits at the bottom. So if I have a slice that has 10 bytes in it, I can pass in 10 right here, and that will give me a bit string with 10 1 bits. And everything else will be zeros. Okay. And so, yeah, it actually does it that way. And so, so this will safely make it so that the compiler will insert an instruction that has fault suppression if that's needed. And yeah, maybe I'll show what that looks like. But here what we have, we assume that we read it into 16 bytes, and we can do a shuffle, which doesn't do much, but it removes that byte 7. And then over here, you can see we shift everything down by 1, and then we remove byte 8. And we shift everything to the right by these numbers here. And we shift everything over here to the left by these numbers. And then we do a bit selection, is what they call it on ARM, where we have some mask. And we say, if it's a 1 bit, we want to take the bit from here. If it's a 0 in the original mask, we want to take the 1 bit from here, and we OR those two together. And so we're just intersplicing the way that it should properly be compressed, because unfortunately we don't have PEXT in SIMD. There is a better way of doing this though, which is we can use a multi-shift instruction. So let's see what that looks like. And let's actually search me.
You don't exist. You lied, it doesn't exist.
That's interesting. Did I spell it wrong? Did I put a thing under? That's my oldest stuff I've ever written.
You can sort by time rather than
Yeah.
best match. It's in the middle
It's a
above
UI
the
Yeah.
results.
I do want to be a little bit careful about what I might have stuck in there, some of my work stuff, but okay, so here's the point. There is a VP multi-shift QB instruction, and this instruction, what it does is it allows you to take a vector which you use as a table, and then you have a vector which you use as indices. And it examines each 8-byte lane independently. And in the indices vector, we're actually looking at bit indices. And so you can specify a number 0 through 63, I think, is the semantics, inside of each byte in the indices. And then it will grab the bits, it will grab 8 bits starting at that position from the other vector. And so what that means is that we can extract the 7 interesting bits of each byte using 2 of these and then interleaving them. So yeah, how that looks, for the first byte, we want to just grab it starting at position 0, and then we want to grab starting at, so yeah, what that would do is it would grab the least significant 7 bits that we're interested in. And then there's that upper A that is the payload that we want to delete. And so in the other multi-shift we would do, we want to start with 1, which will grab 8 bits from this position all the way up to B. And it will move it like this. And so then we have a mask like this, which tells us we want to grab the lower 7 bits from here and that uppermost bit right here. And so this can tell us how to interleave it. Anyways, long story short, you can use 2 of those. You can use VP turn log to interleave those. VP turn log Q is, this is a ternary instruction. And so what this does, it will take 3 registers as input, and one of them has to be an output as well. And then it will take an 8-bit immediate as the final argument. And this immediate is a constant. It has to be embedded in the instruction, like it has to be comp time known, right? And so that 8-bit immediate is actually a truth table. So you can specify a truth table for how to combine 3 vectors interpreted as bit strings. So it will look at each column of 3 bits. How many different combinations can you have of 3 bits? Like how many numbers can you represent with 3 bits? 8. So 2 to the power of 3. 2 to the power of 3 is the answer. So that's why you have 8 bits. And so, because yeah, you have a 1's place and a 2's place and a 4's place with 3 bits. So if you add 4 plus 2 plus 1, you get 7. So 0 through 7, that's 8 numbers. If you have a table that's numbered 0 through 7, that's what this truth table is. And it just needs a single bit of information in each element of this table, which is your 8-bit immediate. And that is how you specify a truth table in here. Now, you don't actually have to write the truth table yourself. The compiler does this sometimes.
So,
Yeah, so if I write export,
sometimes it breaks production.
you know, so I have a vector of what's,
Life isn't fun unless you break production at least every once in a while.
Yeah, once you get that late night call, it's not.
oops,
So are all of these instructions that you're using like exclusive to AVX 512 or other versions for like AVX and 256?
everything that I said for the most latest stuff is AVX 512 only. So multi-shifts and VP turn logs, that's only AVX 512.
Is there anything like that for like on Neon?
Yes. On ArmNeon, you have you actually have 3 bit select instructions. So you can't pass in a truth table, but for the specific situation that I'm talking about, where you do A ANDed with B, oops, ORed with the not of A ANDed with C. What's the problem? I didn't put F in. So yes, you have VP turn log on here. If I make a new compiler and you make it ARM, what's your favorite ARM architecture?
I'm doing V9.
V9.
You know, depends.
Which V9 of what?
Oh, I don't know.
These are your options. Do you have a phone that you use or your
It was
MacBook?
the Apple M4.
The Apple M4?
Yeah.
Let's do that. Okay. I have an M4 in here as well. So this is the instruction I'm talking about. So BSL stands for bit select. There's actually 3 variations of it because it's a ternary operation. And so you have 3 inputs. All 3 of these are inputs, and one of them has to be the destination. You have to overwrite one of them. And so they actually just made 3 different copies of this instruction. The other one is called bit, and then another one, I don't remember what the third one is called. But if you change the order, like if I change this to B and this to A, you see BIF, that's the other one. And if I change, let's swap these again. Same thing. And bit, there you go. So bit, BIF, and BSL, they're all the same instruction, but different order. So yeah.
It's really cool.
Quick question in your BAS function. I see that you have basically, you just manually shifting to the right,
Pretty much.
those numbers. Well, why wouldn't you like at select and then just put 1 through whatever number you want?
Hmm.
Work instead of manually loading it in binary.
Select is for picking between 2 vectors based off of a conditional vector.
Yeah, but you can pass in the second vector as like all empty, and then just select 1 through whatever the first vector, and just pull out what you want.
So it doesn't let you change position of things. You can do that with shuffle, but with select, that's just like I have some condition and I keep some of it or I delete others of it.
Got it,
With shuffle, you might be thinking of shuffle.
okay. Yeah, I think I'm thinking of shuffle. Not
Yeah.
select.
So with shuffle, you can make this undefined, which is a common pattern. I put 0 in here because I use that -1 for that to just pull that 0. So yeah, you're probably thinking of shuffle. And yeah, I am using this to reorient the bytes, but I can't reorient the bits with it. And so you do have to do some bit movement. And if you worked it out, you would see that you have to do this as part of the problem. Another interesting thing I found out in the course of doing this is if you pass in undefined in here, and it, oh, hold on. All right, I was going to say it segfaults the compiler, but apparently it doesn't. There was something that did, and I don't know. I don't know why that just worked. I don't know. That one works. Great job, everybody. Okay, so
That is the Zig experience.
yeah, so like some of them they do throw an error, but then there were a couple things where it didn't properly throw an error; it would just crash. And I'm like, all right, well, somebody should go put the error message in there so people know that you're not allowed to do this, rather than just saying, oh yeah, you did something wrong, figure it out. You know. Anyways, so the other piece of this, if you want to figure out, when you actually read in 16 bytes, one thing that's easier about it is you already have all the information in a single register, as opposed to having to go between two. And so you can more easily do the thing where you say, okay, do a comparison against the splat of OX80. If you want to invert it, you can go this way. And so you can figure out, like, you can make a non-continuation mask this way, right? And you have to specify the type manually because they never added the type inference for that situation yet, which is annoying for me, but probably not annoying to that many people. And then what you can do is you can do a k-add instruction by a bit string of all ones. So this is actually just like some AVX 512 stuff. I don't know. I don't have k-add in this Godbolt. But the point is, we can do a similar thing that we did up here, except in AVX 512, we don't have a subtraction operation on the mask registers. So if you look at k-add right here, okay, this is the list of instructions you have that can operate on k registers directly. You do not have k subtract. You have k add. For some reason you have k XNOR. I don't know how many people are using XNOR out there, but like apparently someone's like, I need XNOR or I cannot use this. It's unusable without XNOR.
Yeah, wait until you make fun of them until you're that guy.
No, XNOR, you actually can use it a lot. The compiler will do it for you. And so instead of doing a subtraction, you can do an addition with all ones, which is the same as adding -1, which is the same as subtracting 1. And so how do you produce a bit string of all ones? Well, k XNOR. So anything XORed with itself is 0. Anything XNORed with itself is 1s. And so so the compiler can do this, where it will insert k XNOR some register with itself, produce all 1s. You can then add that number to something else to subtract 1. And so we can do a similar thing in kind of a roundabout way. We have an and not instruction as well, right here. And so we can basically do the same logic to extract it out, whatever. We can do a shift to put it in the right position. And yeah, we can figure out exactly which bytes we should keep that way. Anyways, I think everyone's done. So,
I didn't know in SIMD that there was different registers for like specifically for floats or for bit masks. Is it that way for like all SIMD, for like ARM or whatever?
so there are specific registers in AVX 512 specifically for masks.
Okay.
And everything else, it's just general purpose or SIMD registers.
Okay.
Floating point numbers use SIMD registers. The reason why there are separate mask registers is it has to do with the implementation in the CPU. If you look into how RISC-V was designed, for example, some people were upset, like Casey Muratori, for example. People were talking about publicly how when you have large vectors, it makes sense to have a separate register space, separate names for the masks. And basically it comes down to performance, it comes down to trade-offs within the CPU of how something is implemented. I don't know if I could find a RISC-V talk off the top of my head that I'm thinking of. Give me 1 second. Okay, I know how to find it. Case Meratory, risk 5 vector. I can probably find it this way.
I feel like top one for wife, age, and Russ.
Right. Everyone wants to know about his wife, apparently. So I think I saw someone link a video on here. That's the one that I'm thinking of. Oh, here we go. Okay. So, in this video, problem with masks is when you want to produce a result, the semantics in RISC-V are that it deposits it into the bottom lane. So if you, like in this example, if you have 8 elements, you're doing some comparison, in this case less than, with another 8 elements, you produce 8 bits of information. Where does that go? The semantics of RISC-V is that it has to go in the lowest 8 bits of a vector. So there's a vector result, and so this movement literally has to happen in the chip. And so there's a big problem with this, which is on RISC-V, there's a really nice facility where, let's open it up. Let's go to RISC-V64, and let's go to, let's go to the X280 that supports 32 bytes.
Pull that up so you can see it.
Click output, and yeah, not every compiler gives you a list like this. So thank Andrew Kelly that this one does. Just saying. All right. Did I mess something up here? Oh, it's just over here. Okay. So if we have a vector of, let's say, 32 U8s, and we want to produce a U32, and we say return A equals this vector splat. What character do you guys want to look for? What's your favorite character? W. Let's go with W.
For the win.
For the win.
I thought that was.
Okay, so first of all, just so people are familiar with reading these errors, it says expected a U32. That's because that's the return type. But we found a vector of 32 bools. So how would you solve this? I'll open this to the crowd. Bitcast. Okay, so some of this is ABI stuff that wouldn't appear in real code. So ignore this and this. Again, I don't know why it's even showing that. It used to not. But what is it doing? So this is our W. It's 119. We're putting it into A0. And we're setting, we do vset VLI, which is, it is a settings changing instruction. And then this is a loading instruction. So we're loading the stuff at A0. So this is actually not pulling it out of a register, I think. It's pulling it from a memory address. And it's putting it into V8. And then it's putting W into A0, which I think is a general purpose register. I don't know if I'm wrong about that. Let's ask our Lord and Savior.
Or don't you just sign in so you don't have to have that?
Well,
So we should make a Brave plugin to discard that.
I think I'm signed into my other browser, but
Yeah,
okay.
I'm gonna have to make that plugin
General purpose.
where it automatically clicks the button for you, so you don't have.
No. Okay, it's a caller saved argument. Yeah, so they have special names for some stuff. So it's the same as X10. Great job, everybody. I don't know. Some people think that's cool. Okay, so it's X10. They put W in it, and then we do an equal each, and that's going to go into the lowest 8 bits of V8, or sorry, 32 in this case, 32. And there's another feature, which is that we can extend this to be very large. We can make this 256, and we can bitcast this to, let's do like a vector of 40, let's do 8 U32s. and thinking about if I did my math wrong. I did my math correctly, but I think the type system is mad at me still.
I guess that has.
In big cast is a big cast.
Am I getting this wrong?
The vector U32, U8 in the inner NAS.
Oh, that's not big enough. That's supposed to be, that's 32 bytes. 256 bits is 32 bytes.
Shouldn't you have 16 and 32? Or?
Maybe. Hold on a second. So, okay. Oh yeah, you're right. I didn't change this. I have to change this. That's why. Okay. So, you'll notice this code doesn't look that different. It's almost the same. And the reason is because this vset VLI right here, this settings instruction allows you to group groups of vectors together. And so when I say right here to compare equal V8 against this one here, this W, this is actually going to take V8 and V9 and V10 and however many. You can do up to 8. You can group up to 8 registers and deploy all 8 of those compare equals in a single instruction. And all of them have to go into this V12. So you're going to fill up V12 with a bit vector for all 256 bytes that we checked. You now have a 256 bit vector that you're storing it in. Now, I would not want to be a hardware person who has to implement this.
Don't the instruction set is reduced.
Maybe. I mean, the other thing about it that he talks about is that you have a ton of sources for all of this stuff, and you have implicit sources too, like implicit mask source. And so this is a problem. Yeah, like I know, for example, on x86, if you tried to run 4 VP turn log queues in a single instruction, even if you have the ALUs to do it, you couldn't, because there are 3 inputs to each of those. 3 inputs times 4 instructions, 12 inputs in one cycle. The CPU cannot deliver that. On x86, you can deliver 10 inputs per cycle. And so you actually can't run 4 of those, even if you have the ALUs that could actually execute it. You cannot put the inputs in there in one cycle. And so yeah, that's one thing that he talks about in this talk, is that if you have a ton of inputs, which you have implicit inputs going on here, then that can be difficult.
Well, time's up.
Time's up. All right.
Time's up.
Other stuff to remember?
Nice 5 minutes.
All right. I appreciate everybody listening to my 5-minute talk.
Tad over
On
on that.
that VSET VLI,
was
it
great.
just makes me think I've never seen so many operands for an instruction. Is that, like, what's the most?
Yeah. I don't exactly know what the encoding of this is. In terms of the thing that has the most inputs, I mean, this is probably it right here. I mean, I don't know. Some of these are baked in. Like, these are not all registers. Some of them are. Like, A2 is a register. I actually haven't spent that much time with RISC-V, the vector part of it. But yeah, this is probably the longest one that you can see. There is another variation of VSET VLI that has an extra letter. But yeah, if you go to vector, yeah, let's do RISC-V spec. So if anyone's interested. Of course, they don't make it number 1, just to be mean.
It's probably great SEO.
Yeah, here we go. No,
Like DuckDuckGo SEO is really bad.
we could try Google.
That's, assume.
If it doesn't work
AI
in
is gonna-
Brave,
I know.
it's not gonna work in Google.
Well, they ruined
There you
Google
go.
now, because the far left is the AI mode thing, and I hate it
Mhm.
every time.
Here you go.
Like, this is so dumb.
So this is the RISC-V
Can't you
V.
turn off AI mode? It
Spec.
asked me and I told it no, and so I don't think I have it.
So if you do want to learn RISC-V, you can come here, and the full specification is here. Good luck.
Good question. What do you think the future is? Is it just going all from SIS to RISC?
I don't think so, because a lot of people who don't know much about the subject look at something like Apple's silicon being very efficient and say that must be because of RISC. Really, it's because of a few things. One, Apple bought all of the stock for the best process node from TSMC, so their competitors don't have a fair fight. That's part of it. They went for the node that's better for efficiency as opposed to the node that, the idea was higher clocks, more performance. That's another part of it. The actual savings that RISC machines have is in the front end of the CPU. So when it comes to instruction decoding, I think most people are aware, on a CISC machine, you have variable length instructions. And so how do you figure out where the third instruction from now starts? Well, it's hard. On a RISC machine, everything is the same size, which can be less efficient in terms of size, but in terms of looking ahead, it's trivial to say, what's 3 instructions from now? I just do 4 times 3, And yeah, so the decoders is much simpler on an ARM machine. However, a lot of the things that CPUs do under the hood are mostly the same. The decoder is just the front end of the CPU. Everything else, like the scheduling part of the chip or the execution part of the chip, in many cases they're running the same floating point units. They're running, they both have giant caches and buffers to feed micro-ops from, and they both have, they both have to do something to do reordering for an out-of-order architecture. They both have a ton of complexity in them, and the decoder is complicated on x86, but also they've worked on adding predictors, which can predict how long a set of instructions will be. They can also do like an n-squared implementation in the hardware, where they say, we're just going to speculatively decode from this position and this position. We don't know which one is right yet, but we can get the results that we want and throw away the work that was unnecessary. And so there are tricks to make that better. In my view, like the decoding length that ARM, the amount of instructions ARM can decode, that's more than x86, that can be compensated from on the x86 side by just caching the micro-ops and saying, when we're decoding right here, just feed from the cache, which is what they do. And there's actually a bunch of different kinds of caches that do this. And so, to me, that's not the biggest problem facing CPUs. And yeah, so in terms of like where I think it will go, I think a lot of people are turning towards efficiency, and historically, for cultural reasons, ARM has been going towards that, because they started out in the embedded market and on low power devices, and ARM obviously has moved more towards performance more recently. But I think x86 has a similar story. They started out only going for high performance, how much frame rate can you get in a game, how fast can we accomplish something, and now they're caring more about efficiency. I do think everyone's going towards efficiency, but I don't think that means x86 will be discarded.
Okay, so we've got about 27 minutes until the heat death of the universe. So if there was anything else that you wanted to do in your existence, go ahead and do it now. But actually, so I'm going to cut in on behalf of some people online. They want to know why there's no video.
I don't know.
It's because they're on Twitch. Okay. Okay, now they've moved to YouTube. And the next question is, can you ask him to share the slides of his last talk and put them in the description or something, please? It's not on his website. I already looked there. It'd be amazing if he could just do it again because the whiteboard talk wasn't very clear.
I will do that one again.
Okay, great.
That's my next one. Next month.
Is that
I wasn't planning to give this talk today. This was just off the cuff. So to people watching, we were not aware of that. This was not a prepared talk.
Oh, yeah, I don't think anybody knew that.
Yeah, I mean, I don't think anyone assumed that it was a prepared talk, but I'm just saying. What was your question?
Oh, were you gonna put up the link to the series of talks you gave, or were you gonna put the link to the
Yeah, my website is validarc.dev.
Yeah, but it's missing that talk. It's missing those slides.
No, he pulled
This
it up
one?
from his- Yeah.
No, the other one, the one from last time.
Got it.
I didn't have slides on
Also,
this one.
your site map,
I think you're talking about this.
404s, huh?
I
Let's
think you're
see.
talking about this.
Let me, I kind of paraphrased a little bit here. Let me make sure. The one about the parse tree representation.
Yeah.
Which one is that? Is that in there?
So with the whiteboard one, I cannot give you slides for a whiteboard. But if you're
No,
talking about this
ask him
one,
to share the slides of his last talk and put them in the description or something, please. The one about the parse tree representation and stuff.
yeah,
I'm thinking, to me, when I think about that one,
there's this one.
all right, well, maybe he'll chime in and say, what about that one where, well, I guess, what's the one where you have it fold over and animate and fold over again and animate, fold over again, the one that was the search algorithm? Maybe, but I guess that's not parse tree representation.
Yeah, definitely not.
No.
But that would be my dynamic score decompose try data structure.
Okay, so that one's yeah, okay. Yeah, that's not parse tree. Yeah.
Yeah, if he's talking about the 5 slides from the whiteboard one,
Yeah, that's
I
what he's
mean-
talking about. That's what he's talking about.
I'm gonna redo that talk.
Don't gaslight him.
So I'm gonna redo that talk next time. Don't worry.
He's
Don't-
going insane.
Tune in next
Don't,
month
don't
for
gaslight
more.
the viewers, man.
Okay.
We've got 7 today. That's more than we've had.
Wow.
See, when you just
That's crazy.
drop the surprise bomb on them, when it's like, we don't know what we're doing this month, and then all of a sudden out of nowhere, boom, Miles. It's like people get excited when they know it's coming. Like they get a
Yeah.
little bit, apprehensive, and they're not sure what to do.
Yeah, we get my hate comments, and
Yeah.
people are like,
How long did it take you to edit that, by the way?
probably too long.
Seems like
Is that with your animation framework you wrote?
I don't know if this one.
Yeah, that's what I thought when he did the thing earlier with the underscores or whatever. I was like, oh, dude, he should be using.
Yeah, that one was custom.
All right, so you have, and this is, I'm not sure if it's like a formal command or if it's more casual because it's got an exclamation mark at the end, but it doesn't have a proper capital letter at the beginning. But it says redo it.
Okay,
So your tech buddy says redo it.
I will. I will.
Okay.
Next month. That's my
Okay,
big. That's
next
my big.
month.
Next month is May, unfortunately.
Is who?
May.
You're going next
Yeah.
month? Okay. That's not what we were planning though, but that's okay.
Well,
I didn't realize this.
A is a
Yeah.
4-letter word,
Oh, yeah.
and B is a very loose term.
Oh.
But, okay, no, is that what, were we planning it next month? I might have
I can do the month after too.
You wanna do the month after? Alright, sure.
Yeah.
Okay. Well, last time I had that conversation with somebody, well, I haven't seen him since, so. Very offensive.
Yeah. You're just an offensive person.
Yeah, well, that's true, that's true. And I
That's,
can
that's why we
sleep-
see different people here every time.
I can sleep easily at night. Okay.
I mean, it's kind of like a rotating cast.
Yeah.
It's like we offend somebody, they're gone for 3 months, and then they come back.
That's good. That's the way that it needs to be. All the best people are on YouTube anyway.
That's true.
Yeah, that one guy that's on Twitch right now,
Yeah.
offend him, get him out of here.
Too many.
Unless Twitch is working for him, in which case he's welcome to stay there.
Too.
Okay, so, no, but, all right, let's, because last time I didn't put dates next to the schedule, so let's go ahead and put dates next to it, so Robert, if he gets back to me, I don't think I have any way to contact him other than I have his phone number that I messaged him on once, and.
Was he the guy who was here last month? Like the new guy?
No, no, Robert, he, I think works at either UPS or FedEx, I think it's FedEx, because I think he has a purple shirt
okay.
sometimes when he comes, and they're
Curly hair.
kind of curly hair.
Yeah.
Yeah,
Normally sits right over there.
yeah, he's also interested in some game stuff, I believe.
Okay, so this check, okay.
So, anyway,
Yeah, stand up.
yeah, he,
Get out of his chair.
yeah, he was gonna present on something, but then we didn't get firm on it, and then I don't actually know what his handle is. Oh, no, I do have his handle on here, I need to have a spreadsheet for what people's real name is, like, 'cause Andrew's the only one that makes sense. His is just wait, what do you call that?
I don't know. It's a mangled version of my actual
A
name.
balderdash?
I don't know. Yeah, it's Druid Ghost Sage because I'm Andrew Gossage. So.
Yeah, I know, I get
Yeah,
it.
but
Everybody else seems to
Madlib.
Madlib.
Yeah.
No, Madlib is the one where
You fill
you fill in the blank.
Oh,
I think it's balderdash.
it might be.
I have to
How about like
check.
a ear corn or something?
Baldur's Gate.
Yeah, that's right, you got it, you got it.
All of you three.
Egg corn.
Okay, so anyway, so let's get this line up then. So we've got, how many more 5-minute presentations do you have for the year?
I was thinking like 12 next time. I'll just like speed run them. Yeah.
Okay, last time
We
you,
just start at 6
last
a.m.
time,
and we'll-
last time you speed ran a presentation, I think it took 3 hours. So I recommend not speed running it.
All right.
I
Yeah.
think you should use the text thing on your presentation.
I'm glad you got what PEX does, so that's great.
Okay, but seriously, so we've got August is coming up next for those that don't do calendars well. August, September, November, December. So November we're safe because we're the second Thursday of the month. December we should be safe as well. I mean, as safe as an unsafe meetup can be. So we've got
The rest people are over there, all right?
September.
If you want to be safe, go to the rest meetup,
That's right.
all right?
That's right.
Are they still doing that?
Yeah,
I think they.
they're there
I
today.
think they got out like half an hour or more ago.
They've got like a structure or a schedule or something.
Yeah.
Listen, that's the hardest part of the
You
project.
know, I went to the remix meeting a couple times now, and it's like 30-minute talk and then done, and then weird like 3 hours, and it's way better here.
That makes my heart swell with joy. Here's to the whatever ones. the square pegs in the round hole. Anyway, so August. Let's just fill it out because I think we've got. Wait, all right. 1, 2, 3, 4, 5, 7. Yep. Okay, that's it. That's 12.
If both of you want, and then it just said no.
All right. So
I can volunteer to talk because they're trying to.
yes, that's what I want. But I need some contact details too. I'm going to go ahead and turn off the online thing. If there's anybody else who wanted to. Okay. Yes, Tech Buddy made it more clear. He put extra exclamation marks in caps. Redo. This is an order. And remember, he's someone on the internet.
Okay.
He knows our IP address.
I don't think he does, but I will watch out.
So you better do what he says because he'll cut you.
What's the handle again?
Tech Buddy.
Tech Buddy.
Yeah, you watch out for Tech Buddy. When you cross the street at night, I hope you look both ways.
All right.
All right, I'm getting video download canceled. Please try again. Yeah, that's just Twitch is that way. I don't know why Twitch does that sometimes. I even changed the resolution so it wouldn't do that because it was doing that because it was 2K instead of 1080p because they support different resolutions, but 2K it works sometimes. But yeah. All right. It's only a broken stream. I can't watch on Twitch. How is this even possible? Yeah, I don't know. Maybe the bitrate's too high. I can look into it again, I guess. But I thought I changed it so that Twitch would work for mobile Twitch as well. But it'll work on desktop Twitch, but not mobile. Yeah, some issue with the restream setup. Yeah, it's
OBS.
yeah, something like that.
Bitrate.
Use text.
Yeah, so if you click on recent broadcast, you can watch it. All right, so there's no more comments there. All right, so I'm gonna cut off the online. Thanks for
Gotta
joining
cast
in.
your bit rate.
Sounds like a skill issue. Like, yeah, if Twitch isn't working for you, says the one who left Twitch to come to YouTube, by the way. Yeah, so I'm going to go ahead and end the stream. Thanks for joining in. Thanks, everybody, for coming here. Thanks to Niles for giving us something to do this evening.
Of course.
All right.
Thank you, everybody.
All right, and now on to official meetup business.